Chapter 3, probability. What is probability? Probability is a machine. It is a function. Probability as a function. So what you do, you plug in some values like x. It gives you P of x, probability of an event or a number. The most important characteristic of this function is the outcome values are numbers between 0, 1 inclusive. So it means that you can have probability of x equal to 0, probability of x equals to 1. You can also have probability of x equals to a half, a third, a fourth, 1/10, 2/9. Any number, any fraction, any decimal that is in between 0 and 1 is an acceptable probability. Note that you do not have probability equals to -1. You do not have probability greater than 1. Very well, when it comes to probability, we need some basic definitions. The first definition is definition of an event. An event is any collection of results or outcomes of a procedure. So you gather some numbers together, some values, some outcomes, and you call it an event. A simple event is an outcome or an event, just one outcome or one event that cannot be further broken down into simpler components. The sample space for a procedure consists of all possible simple events. So when you list all simple events, then you define your sample space. That is, the sample space consists of all outcomes that cannot be broken down any further. Very well, let's go over one example to see what's going on. So in the following display, we use B to denote a baby boy. So B for baby boy and G for a baby girl. So suppose the procedure is a single birth. Example of an event, one girl. The sample space or the list of all possibilities is going to be either a boy or a girl. So this is your sample space. Remember that for a sample space, you have to put all the values, all the outcomes inside curly bracket. The second procedure is 3 birds. Okay. You can say an event can be having 2 boys and 1 girl. So 3 birds, 2 boys, and 1 girl. What is sample space for the list of all possibilities? 3 boys, 2 boys and a girl, 1 boy, 1 girl, 1 boy, 1 boy, 2 girls, 1 girl, 2 boys, girl, boy, another girl, 2 girls and a boy, and 3 girls. This is the collection of all possibilities. This is your sample space. So your sample space has, in the first procedure with single birth, your first sample space has only 2 elements. You can write, okay, S as the sample space equals to boy and girl. N of S, or the total number of values in the collection, is 2. The second procedure has sample space S equals to boy, boy, and boy. I'm just repeating this collection here. How many do you have? You can actually see you have 1, 2, 3, 4, 5, 6, 7, and 8. So you write N of S equals to 8. The total number of values in your collection. In the first sample space, you only have 2 outcomes. In the second sample space, you have 8 outcomes. You can denote it by N of S, the number of values in S. So N of S the number of values in set S. If you write N of A, it means that you're counting the number of values in set A. So the number of values in set A. We can have many different sets. Let us move on to next page. Relative frequency approximation of probability. Okay, suppose you have a procedure and you count the number of times that an event like A actually occurs. You can define the probability of that event by forming this fraction. It has a numerator, it has a denominator. On the numerator, you just write number of times A occurred. On the denominator, you actually count the total number of times that the procedure was repeated. So it is equal to N of A divided by N of S. S is the sample space, includes all possible outcomes. In classical approach to probability, we can actually say that probability of event A is the number of ways A occur divided by the number of different simple events. S over N, or N of A divided by N of S. So these are the formulas that you're going to use to calculate the probability for an event. We're going to go over some examples to feel more comfortable about this topic. Very well. Note that P denotes the probability, A, B, and C denote specific events. P of A denotes the probability of event A. Okay, take a look at this example. A recent Harris Interactive survey of 1,010 adults, so in total you have 1,010 adults in the United States, showed that 202 of them smoke. So here you have a survey, here you have a sample of 1,010 adults, and it turned out 202 of them smoke. It's a sub-collection or subset of your sample. Find the probability that a randomly selected adult in the United States is a smoker. Perfect. We just learned a new formula. We learned that the probability of an event is equal to the number of times that event occurs divided by the total number of entries, outcomes in the procedure. So how many smokers do you have in total? 202. It goes on the numerator. What's the sample size? 1,010. You do the division and you have 20% or 0.20. Is this number in between 0 and 1? Yes. So it means that our probability is correct. Always check to see if the outcome value is between 0 and 1. If it's greater than 1, it means that you made a mistake somewhere and you have to get back and correct it. Very well. Okay, another example. So when 3 children are born, the sample space of genders is as shown in example 1. In previous example, we saw that we can form a sample space like this set. So S, or sample space, has 8 elements. If boys and girls are equally likely, then the 8 simple events are equally likely. That makes sense. Assuming that boys and girls are equally likely, find the probability of getting 3 children all of the same gender when 3 children are born. So 3 children. The probability of 3 children of the same gender is equal to, they are either all boys, 1, or they are all girls, 2. So you form a fraction. On the numerator, you have 2 possibilities. On the denominator, you have all these possibilities in your sample space. 2 divided by 8 is 0.25. Is 0.25 a number between 0 and 1? Yes. So I'm good with my probability. Subjective probabilities, PA, the probability of an event A is estimated by using knowledge of the relative circumstances. For example, note that the classical approach requires equally likely outcomes. If the outcomes are not equally likely, we must use relative frequency approximation, or we must rely on our knowledge of the circumstances to make an educated guess. Take a look at these 3 figures. Okay, an accident, a lottery, a disaster. Relative frequency approach, when trying to determine the probability that an individual car crashes in a year, we must examine past results to determine the number of cars in use in a year and the number of them that actually crashed. Then we find the ratio of the number of cars that crashed to the total number of cars. For a recent year, the result is a probability of almost 5%. 5%. B. When trying to determine the probability of winning a grand prize in a lottery by selecting 6 numbers between 1 and 60, each combination has an equal chance of occurring. The probability of winning is actually very close to 0%. Which can be found by using methods represented in the rest of the chapter. Okay, let's see, we have a question in the chat. Let me explain this, then I show you the definition. And finally, subjective probability, when trying to estimate the probability of a passenger dying in a plane crash. We know that there are thousands of flights every day, but fatal plane crashes are quite rare events. So the probability is very small. A good guess would be about 1 in a million. Again, a number which is very close to 0. So Raul asked for the definition. Here you are, subjective definition. Okay. For example, what's the probability that you will get stuck in the next elevator that you ride? Okay, so in the absence of historical data on elevator failures, you cannot use a relative frequency approach. There are 2 possible outcomes: becoming actually stuck or not becoming stuck in the elevator, but they are not equally likely. So we cannot use the classical approach. That leaves us with a subjective estimate. In this case, experience suggests that the probability is quite small. Let's estimate it to be, say, very small, okay. It's almost 0, 1 in 10,000. So the subjective estimate based on our general knowledge is likely to be in the general ballpark of the true probability. So very small, almost 0%. Let us talk about the complementary events. Sometimes you need to find the probability of an event like A that doesn't occur. So we call that the opposite of that event is called the complement of event A. We denote it by A bar or AC or sometimes A prime. So if you open a different probability book, statistics book, you might see these representing complement or opposite of an event. A bar, A complement, A prime. It consists of all outcomes in which event A does not occur. So that's the definition of a complement or opposite of an event. Very well. Some important principles and notation for probability. First of all, you remember that the probability of an event is a number between 0 and 1. If that probability or that event is not between these two numbers, it means that you made a mistake and you have to get back and check the algebra. The probability of an impossible event is 0. So probability of an impossible event. What's an impossible event? Like a cat sitting in this class learning statistics. Probability of a cat learning stats is 0. Impossible event. Probability of an event that is certain to occur is always 1. Again, the probability of an event like A is denoted by P of A. So you expect to have the probability of the opposite of that event or the complement to be P of A bar. So what's the relation between PA and P of A bar? These are the types of questions that you should be asking. We're going to see a connection between them. Please take your time. Let us continue. So previously, we talked about basics of probability and considered events categorized as simple events. Now, what if we have compound events? What's the meaning of that? It means that we have, for example, two events like A, B, we're connecting these together by AND, or we're connecting them by OR. A or B. So here's a question for you. Have you seen union intersection before? Let's write a quick note for you. Union of two sets, A and B, is denoted by A union B. It includes all values in set A, set B. So when you're talking about OR, you're actually talking about the union, A union B. Other than union, we have something that we call intersection. So this is the union, intersection. Intersection of two sets A, B is denoted by A upside down U, B, which is all common elements. So you find all common elements between A and B, and you call it the intersection of A and B. It turns out when you're talking about a compound event like A and B, you're talking about their intersection. A intersection B. So what is our goal? Our goal is to find the probability of compound events.
Professor, I had a question.
Go ahead.
For the intersection of two sets, I see that you did, for the union of two sets is A, U, B. For the bottom, is it A and B?
A intersection B.
Oh, is that like a...
Upside down U.
Okay, okay, thank you.
Sure. So for intersection, if this is set A, this is set B, the intersection is going to be the overlapping part between these two sets. When you're talking about union, you have to include everything in A, in B. That's the union. Very well. In general, we say that a compound event is any event combining two or more simple events. Notation for addition rule. The probability of A or B is the probability that in a single trial, event A occurs or event B occurs or they both occur. That's the meaning of that. That's the interpretation. So how do we calculate using the probability formula? Probability of A or B is equal to probability of A plus probability of B minus the probability of their intersection. So P of A union B is P of A, probability of event A, plus probability of event B minus probability of their intersection. We learned that probability is a function that is represented using fractions. So it is n of A, the total number of values in A, divided by n of S plus n of B, the total number of values in set B, divided by n of S, minus, you count all the values in the intersection, divided by n of S. So that's the meaning of this formula. Suppose you have set A equals to 1, 2, 3, 4, and 5. I have another set B, which is equal to 4, 5, 6, and 7. I say, very well, what is the probability of A or B? What is this probability? So first of all, you should be asking, what is S? What is my sample space? Suppose I say your S is equal to this big set, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is my S. I give you a sample space. I give you two sets that are subsets of your sample space, and I ask you find the probability that A or B occur. First of all, we have a formula. This formula says P of A or B is P of A plus P of B minus the probability of their intersection. Mathematically, P of A or B is equal to P of A plus P of B minus P of A intersection B. Okay, so P of A union B is equal to P of A. But what is P of A? How many elements do you have in A? I have 1, 2, 3, 4, 5 elements in set A, divided by, what is my sample space? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plus, what's the probability of B? How many elements do I have in B? 1, 2, 3, 4, divided by n of S. How many data do I have in my S? 10. Minus the probability of their intersection. So what is intersection between A and B? How many elements are common between A and B? A intersection B.
Would it be 2, the 4, and the 5?
Very good. Excellent. Thank you. A intersection B is a new set including all common elements, 4 and 5. These two elements are repeated in these two sets. So minus the number of values in intersection is 2 divided by n of S, which is 10. If you do the algebra, they all have the same denominator, so you can write one denominator, 5 plus 4, 9, minus 2, 7. So the probability of union between these two sets is 7 out of 10. Very well. Definition of disjoint or mutually exclusive events. They say that two events like A and B are disjoint or mutually exclusive if they cannot occur at the same time. They don't have any overlap. There is no intersection between them. The intersection between them is empty. Like what? Like being single and married at the same time. Being single and married. It's impossible. So the probability of such an event is 0. Then you have disjoint or mutually exclusive event. Its probability is always 0. It's not like those Facebook status, it's complicated. It's math. So when it comes to mutually exclusive or disjoint events, for sure you say that the probability is 0. Very well. If you add the probability of an event and its complement, the outcome is always equal to 1. The probability of event A plus the probability of the complement of event A is always 1. So we can use this formula to drive two other formulas. If you subtract P of A from both sides, P of A complement is equal to 1 minus P of A. If you subtract P of A complement, the probability of complement of event A from both sides, you can find probability of event A by subtracting the probability of its complement from 1. Let us move on. Okay, here's an example for you. So, following table summarizing results from a study of people who refused to answer survey questions. I hear you knocking, but you can't come in. So this is the resource that you can use. Perfect. So first of all, they categorize the respondents or non-respondents by age. The first category, 18 to 21. This is your first category. How many responded? 73, and refused to respond, 11. The second category, 22 to 29. Responded, 255. Refused to respond, 20. The third category, people who age between 30 to 39. How many responded? 245. Refused to respond, 33. Age 40 to 49. How many responded? 136. How many refused to respond? 16. Next category, 50 to 59. How many responded? 138. How many refused to respond? 27. And finally, 60 and over. How many responded? 202. How many refused to respond? 49. Now, here's some questions for you. What is the probability that the selected person refused to respond? Refused to respond, okay. I have a bunch of numbers here that shows that refused to respond. What should I do? I have to add all of these numbers together to find my numerator. So, probability of refused to respond. Refused to respond. First of all, you have to form a fraction, definitely. On the numerator, you have all these people from different age brackets that refuse to respond. 11 in the first bracket, 20 in the second bracket, 33 in the third bracket, 16 on the next bracket, 27 on the other bracket, and finally 49 on the last bracket. What goes on the denominator? All of the people who responded or refused to respond. 73 plus 11, 255 plus 20. And you have to keep going. 202 plus 49. This is your denominator. All people in this survey either responded or refused to respond forms a sample space. So if you add all of those numbers on the numerator, you get 156. On the denominator, you get 1205. If you do the division, the probability is almost 13%. Almost 13%. 13% of the sample refused to respond. Let us move on to part B. Okay, we're answering part B, so let us erase this. Part B says, a pharmaceutical company is interested in opinions of the elderly. because they are either receiving Medicare or will receive it soon. What is the probability that the selected subject is someone 60 and over who responded? Okay, guys. First of all, age category, age bracket is 60 and over. Who responded is the intersection. 202 people age 60 and over responded. That goes on the numerator. Divided by, okay, on the denominator, you have the total. All of the people who either responded or refused to respond, which is 1205. If you do the algebra, you get almost 17% from your data. So let us erase this, then move on to next part. So we have age brackets. Now for next part, part C says, what's the probability that the selected person responded, or, the keyword is or, is in the 18 to 21 age bracket. Remember that when you have or, it means that you have union. P of A union B is P of A plus P of B minus the intersection. Okay, what is A? A is responded. What is B? B is belonging to age bracket 18 to 21. So P of A responded. How many people responded in this collection? How many responded? 73, 255, 245, 136, 138, 202. So the probability of responded is the sum of all of these numbers, 73, 255, plus, dot, 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 138, 202, divided by the total number of values in your collection, 1205. So if you add these numbers together, you get your first fraction. The probability that you randomly select a person and that person responded. So we're done with P of A. Plus P of B. P of B, what is B? B is 18 to 21. 18 to 21. So how many people are in age bracket 18 to 21? We don't care if that person responded or refused to respond. The total is 84. 84 out of the total number of people in your survey. So we're done with P of B. Lastly, the intersection. Now, what is the probability of a person who responded and also is in age bracket 18 to 21. P of A intersection B. In age bracket 18 to 21 and responded. The intersection is 73. 73 out of total, which is 1205. So we found all of these three probabilities. Now we do the algebra by adding and subtracting these numbers. 1060 divided by 1205, which is 88%. Is this number between 0 and 1? Yes. It means that our calculation is correct.
Wait, Professor?
Okay. And finally, D. What's the probability that the selected person refused to respond or is over 59? Again, you have a keyword or. It means that you have union. The first event, refused to respond, A, over 59, B. So P of A union B is P of A plus probability of B minus the intersection. Again, we have to look at the table and calculate each of these. Refuse to respond, we don't care the age bracket, so let me erase this. Refuse to respond, the last row, how many? We don't care about the age bracket. These are the numbers of people who refused to respond. 11 plus 20, you actually calculated that in part A, refused to respond. 156, the sum of these numbers, divided by the total, 1205, your first fraction. P of B, they are over 59 years old. How many? 202 plus 49. 251 out of 1205 are over 59 years old. It doesn't matter if they refuse to respond or responded. You need the total. The second probability, and finally, lastly, you have the intersection. As you can see, the intersection between refuse and over 59 is 49. There are 49 people who refuse to respond and they are over 59. You do the calculation, you get almost 30% of them.